A titration curve is a graph which shows how the pH of an acid solution changes as a base is added to it, or how the pH of a base solution changes as an acid is added to it. Here we'll consider the addition of a strong acid to a solution which is initially a weak base. The strong acid we'll use in our example is 0.1 molar HCl, and the weak base we'll use is 0.1 molar NH3. We have initially added 25 milliliters of 0.1 molar NH3 to the beaker. A pH meter will be used to monitor the pH of the mixture in the beaker below the burette. What we'll do is draw a graph of the pH in the beaker versus the volume of HCl added to the NH3 in the beaker. We'll start with the 0.1 molar NH3 solution in the beaker. No HCl acid has been added yet. NH3 is a weak base, so the initial pH will be above 7. It can be determined that the pH of 0.1 molar NH3 is equal to 11.12. This is where the curve starts. As the first 3 milliliters of HCl is added, the pH goes down fairly quickly. From 3 milliliters to 24 milliliters of HCl added, the NH3 is in excess and the HCl is the limiting reagent. The limiting reagent, HCl, will react with some of the excess NH3 to form some NH4+ and Cl-. Because the HCl is the limiting reagent, it will all be used up. And Cl- is a spectator, so it does not affect pH, so we'll discard its formula. The HCl will react with some of the excess NH3 and will be left with less than we started with. So during this portion of the titration, we have some weak base left over, but we have also formed some of its conjugate acid, NH4+. Recall that a mixture of a weak base and its conjugate acid forms a buffer solution. A buffer solution minimizes the change in pH as HCl is added to the mixture in the beaker. So because of this buffering effect, between 3 mL and 22 mL, the slope of the curve is less steep. As we go from 22 milliliters to 25 milliliters of HCl added, the buffer solution is overcome, and the pH falls steeply. At 25 milliliters of HCl added, we have reached the equivalence point of this titration. In order to understand what we have at the equivalence point, we construct what is called an ICF table. I stands for the initial moles, C stands for the change in the number of moles as the reaction goes to completion, and F stands for the final number of moles of each component remaining. Initially, we had 25 milliliters of 0.1 molar NH3 in the beaker. This is 0.025 liters times 0.1 mole per liter, which equals 0.0025 moles. At the equivalence point, we added 25 milliliters of 0.1 molar HCl, which is also 0.0025 moles. If we imagine a time just before the reaction starts, we have no products yet. HCl is a strong acid, so this reaction goes to completion. In the process, 0.0025 moles of both NH3 and HCl are consumed, and 0 moles of these two reactants remain after the reaction. According to stoichiometry, if 0.0025 moles of NH3 and HCl react, 0.0025 moles of both NH4+ and Cl- will be formed. So when the reaction is complete, we will have 0 plus 0.0025 equals 0.0025 moles of both NH4+ and Cl-. Because the Cl- sign is the conjugate base of the strong acid HCl, it is a spectator ion and will not affect the pH. So we'll eliminate that from our table. Once the reaction at the equivalence point is complete, there is no longer any NH3 or HCl present. So we'll also eliminate these from our table of what is present at the equivalence point. So at the equivalence point, the only thing we have that can affect the pH is 0.0025 moles of NH4+ ion. Looking on the acid table, we see that the ammonium ion, NH4+, is a weak acid. So at the equivalence point, the only species remaining that can alter the pH is a weak acid, which means that the pH at the equivalence point is below 7. Using the fact that we have 0.0025 moles of NH4+ in a total of 50 milliliters of solution, the concentration of NH4+ can be calculated. Remember, we have 25 milliliters of NH3 and 25 milliliters of HCl, which is a total of 50 milliliters or 0.0500 liters at this point. The concentration of NH4+ is 0.0025 moles divided by 0.0500 liters, which comes out to 0.0500 molar. Ice table calculations using the Ka of NH4+ and its concentration of 0.0500 molar reveal that the pH at the equivalence point is equal to 5.28. At this point, it might be good to pause the video and calculate the pH on your own. So the pH at the equivalence point is 5.28. Now we'll add more HCl to the solution and go past the equivalence point. As we add HCl, the pH rapidly drops until about 27 milliliters is added, where it starts to level off a bit. As we keep on adding HCl until the volume added is 50 milliliters, the pH shows a very gradual decrease. Now we'll review the main features on a strong acid weak base titration curve. First of all, the pH at the very beginning, before any acid is added, is above 7, but not really high like 13 or 14. This is because at this point all we have is weak base in the beaker, as we haven't added any acid yet. The buffer region is the portion of the curve near the beginning, when the curve shows a decrease in slope. During this region, we still have a slight excess of the weak base, NH3, and the reaction that has occurred so far has produced some of the weak acid, NH4+. Remember, the combination of a weak base and its conjugate acid constitutes one type of buffer solution. At this point, the capacity of the buffer solution is exceeded, and the pH starts to drop rapidly. The almost vertical section of this strong acid weak base titration curve is shorter than it would be for a strong acid strong base titration curve. In the very center of the almost vertical section, we find the equivalence point. It is important to remember that the pH at the equivalence point of a strong acid weak base titration is always below 7, but not extremely low like 1 or 2. Looking at the balanced equation for this titration reaction as an example, at the equivalence point, the weak base, NH3, reacts completely with the strong acid, HCl. So the two reactants are completely consumed. And all we're left with is a spectator ion, Cl- in this case, and an acidic cation, NH4+ in this case. The solution at the equivalence point of a strong acid weak base titration is always slightly acidic, with a pH somewhere below 7. The actual pH at the equivalence point depends on the strength of the base and the concentrations of the reactants. Right after the equivalence point, the pH drops sharply for a short time, then shows a gradual decrease until the total volume of 50 milliliters of acid is added. Now we can use this graph to find the best indicators for this particular strong acid weak base titration. The pH at the equivalence point of this titration is 5.28, so we look on the indicator table for any indicators that have 5.28 within their pH range of color change. We see that brome cresol green, methyl red, and chlorophenol red all have 5.28 within their pH range of color change. The pH at the transition point for each of these three indicators has been calculated and listed here in red. The pH at the transition point of methyl red, which is 5.4, is closest to the pH at the equivalence point of this titration, 5.28. So methyl red is the best indicator for this titration. Even though methyl red is the best indicator for this titration, any indicator which changes color on the nearly vertical section of this graph would work very well. So that would include any indicator with a transition point pH somewhere between 3.3 and 7.4. The indicators on the table from methyl orange all the way down to neutral red have a pH at the transition point between 3.3 and 7.4, so any of these would be suitable for this titration. Be aware that both the pH at the equivalence point and the location and length of the nearly vertical section of the graph depends on the particular weak base and strong acid pair we're using in this type of titration. The graph for each pair of reactants is unique.